Path of a reaction and the effect of a catalyst. So the equilibrium constant is helpful. It tells us whether the products or the reactants are favored. It tells us the extent of a reaction. It doesn't tell us how fast it gets there. Okay? So in order to understand how fast a reaction occurs, we need to think about the reaction rate. And this is going to be somewhat related to what's called the activation energy, or sometimes called an activation barrier. That's the energy barrier that has to be overcome in order for the reactions to be converted into products. It's a little bit like making an investment. It's hard to make a lot of money without any money to start out with, right? You need like seed money, right? You need a little bit of money to get started in some sort of an investment or a business. I mean, even if you're just mowing lawns or delivering papers, it really helps to have a lawnmower or a bike to ride, right? So you have to invest a little bit. So there's an investment of energy that needs to happen for most reactions to occur. And then in an exothermic reaction, the payout is greater than the investment. But there has to be that initial investment. That activation energy for most chemical reactions occurs because the bonds in the existing molecules have to be broken before the new ones can form. So let's look at this example. Here we have the reaction of hydrogen and oxygen to form water. So here we have two hydrogen molecules and an oxygen molecule. In order for them to recombine, we have to break this hydrogen-hydrogen bond and that hydrogen-hydrogen bond and this oxygen-oxygen bond. We have to break that. That requires energy. That is reflected in this hump here. We're graphing energy up the y-axis and reaction pathway as we go along. You could also think of that as time. So in order for these to react, we have to have a certain amount of energy involved. We talked about collision theory and how in order for things to react, they have to collide. And not only that, they have to collide with enough energy in order for them to react. This activation energy is that energy. Another way to think about this is miniature golf. This graph always reminds me of the greens on a miniature golf course. That's going to be too fat. Let's go like this. So think of this as being green now. There, doesn't that look more like a miniature golf course from the side? And you're up here hitting your ball, and if you don't hit it hard enough, if you don't hit it with enough energy, it goes partway up the hill and it rolls back down, right? And that's really frustrating. You have to hit it hard enough, hit it with enough energy so that it goes and makes it up all the way over. And then after that, gravity will take care of it and it'll go on down the hill. But you have to get enough energy into it. It's called the activation energy. So if the activation energy is high, the reaction is likely going to be fairly slow. So the higher the activation energy, the fewer the number of reactant molecules that make it over the barrier, and the slower the reaction rate. How could we speed that up? In general, at any given temperature, the higher the activation energy, the slower the reaction rate. That kind of just says the same thing. How could we speed that up? Well, we could increase the concentrations of the reactants. So when we talk about the energy that a substance has, it's always an average energy. Just like when we talk about people, we talk about averages, the average age of the population. Well, there's some people that are older and some people that are younger. Not everybody is at the average age, right? And in the compound or the molecules of these reactants, there's an average kinetic energy which is related to the temperature, but some of them are high and some of them are low. So even at a cool temperature, some of them are going to have higher energy and be able to get over. Actually, there's a slide coming up here. Let's look at this. Where'd it go? No. How did I miss that? Well, that slide seems to be gone, so I won't go there. So how can we speed up the reaction? If we increase the concentration of the reactants, we're going to have more collisions, right? And we're going to have more of the energetic particles. We're also going to have more of the non-energetic particles. The average energy is the same, but there's going to be more. And so it will react faster if we just increase the concentration of the reactants. Or we can increase the temperature. When we increase the temperature, the energy of the collisions increases. And this causes the reaction to go faster because more of the collisions are successful. So if we go back to the miniature golf idea, increasing the concentration would be like increasing the number of balls that we're hitting. So here's all the golf balls. And if we're hitting a whole bunch of golf balls and not really paying attention to how hard we're hitting them, we're just hitting them. More of them are going to go over than if we're just hitting one at a time, real slow. Increasing the temperature would be like hitting these balls harder. Same number of balls, but hitting them a lot harder. Now more of them are going to make it over the hump, and that will increase the rate of the reaction. The other thing we can do is to use a catalyst. A catalyst in miniature golf would be like cutting off the top of the hill. Little kid having trouble getting the balls over the hill. Let's just take the top of the hill off. We'll make the hill lower, right? Now more of the balls will go over. And that's what a catalyst does. It provides an alternate pathway. So here's the book's example with rocks on a hill. And you got to push this rock all the way up here to get it to fall down. Or you could find a path around the peak of the hill and push them around this way. And that's going to be a lot faster because you don't have to go all the way up here. It's a lot less energy involved. So a catalyst provides an alternate pathway. So I do have an analogy for that one. I get rid of these words. See if I remember how to get rid of the words. So just make them all gray. So you can see my fabulous drawings. So, don't do that to me. This is a fence. Now it's starting to look like a fence. Okay, there's a fence. I don't know where this analogy originally came from. I've been using it for years. There's kindergartners. And for some reason, the kindergartners need to get over the fence. Now, they're entirely capable of climbing over this fence. It's not like electrified or anything, and it's just a nice wooden fence, and you climb it up like a ladder, and you can climb down the other side. But it's going to take them some time, right? Because they have to climb up and get over. And so it's going to be slow getting all these kindergartners over the fence. How could we speed it up? We could lower the fence. Yep. What if we just take out... Oh, that doesn't work. Okay, let's try it this way. What if we take out part of the fence? We've lowered the activation energy. We've lowered the barrier. Now the kindergartners can get over the fence faster. They can get to the other side faster because they just have to step over that lowest bar. Another possibility is we could get a teacher to stand here and pick the children up and lift them over the fence. Okay, so that's another option. It's an alternate pathway that's lower in energy for the reactants, and so it makes the reaction to go faster. So here's that energy graph again. Here's energy on the y-axis. Here's our reactants, and here's our products. There's the original activation energy. By adding a catalyst, we've shaved off most of that hill, and we've made it much easier for the reactants to actually react. And that's what a catalyst does. Catalysts are really important in biological systems. They're called enzymes. And enzymes are really important. In a biological system, you can't just be messing around with the temperature. You know, you can't say, oh, well, we need things to go up to 150 degrees Celsius so that we can get this reaction to go at a reasonable rate. Okay, your body's going to get cooked. It's not going to work. Many biological compounds and many chemicals in general are thermally sensitive. And so you can't just heat them up, and you can't necessarily increase the concentrations either to get the reaction to go faster. A lot of biochemical reactions proceed so slowly without a catalyst that the organism would not survive because the reaction doesn't happen fast enough. And so enzymes are used in your body and most organisms to catalyze reactions. An example of a reaction that's catalyzed by an enzyme is the metabolism of sucrose. Sucrose is a disaccharide. It's composed of glucose and fructose bonded together. And your body wants to break those apart so that it can use them to do things, make energy out of them. It sends the glucose around in your blood to supply energy to your cells. There's an activation energy, though. And so at physiological conditions, this reaction goes very, very slowly, and the cells are not going to get the energy that they need. By using an enzyme called sucrase, this provides a lower energy pathway, like the teacher lifting them over the fence. It makes it easier, and so it speeds up the reaction. And here's an illustration. So here's an illustration of a sucrase molecule. These are large protein molecules, and we don't really care exactly what their structure is or anything. We just are interested in what they're doing. They have what's called an active site. And I like to think of this as the big spaceship, and it's got this landing pad here, a docking station, you know, and the spaceship comes in and it can dock. When I say docking station, that reminds me of iPhones and iPhone charging stations and, you know, the little iHome thing. And you've got an iPhone 4S and it fits in there, and then you upgrade to an iPhone 5S and it doesn't fit anymore, does it? It doesn't. Only certain things fit in there. It has to have the right shape. And that's how these enzyme active sites are. Sucrose fits into this active site on sucrase, the enzyme. Other sugars like maltose do not. They don't fit. Just like the iPhone 5S does not fit on a docking thing for the 4S. Even though they both have S in their name, it doesn't matter. Well, what happens? The sucrose comes in here, and it just fits in here like a glove. It just fits in perfectly. It's like almost like a Lego brick, just snapped. In this particular instance, what happens is when the sucrose comes into this active site, this bond becomes weakened. It gets stretched and pulled on a little bit. It gets weakened, and now that bond is easier to break. It takes much less energy for that bond to break, and so it breaks at a faster rate. After that bond breaks, these guys go off on their own. The sucrase says, okay, job done, go off, run along now, next, and then another one comes in. The enzyme catalyst is not used up in the reaction. It's not one of the reactants. It participates in the reaction, but it doesn't actually react. So it's like the teacher helping the students over the fence. It just takes one sucrose molecule after another and helps it to react, sends it on its way, and then takes on another one. And your body uses enzymes in just awesome ways in your body to control the reactions that are occurring in your body. Okay, so that's the end of chapter 15. Those are the review slides.